In this video, we're going to cover sections 10.7 and 10.8. 10.7 deals with carbon nucleophiles, and 10.8 deals with synthesis strategies involving reactions that we covered in this section. As we saw in the previous video, we can use hydrogen nucleophiles to reduce aldehydes and ketones, esters, and carboxylic acids to form alcohols. In this section, we're going to talk about carbon nucleophiles, which also results in the formation of an alcohol, but we also increase the amount of carbon in our product compared to that of the reactant. Now, the most common carbon nucleophiles are the Grignard reagent and the organolithium reagent. And both of them can be produced from a reaction with an alkyl halide. So if we take an alkyl halide and react it with magnesium, what will happen mechanistically is that the magnesium will insert itself between the R group of your original alkyl halide and the halogen. Now, the mechanism for this reaction is still being explored to this day, but it's involving radicals for the most part. Similarly, if we take lithium and introduce that to a alkyl halide, we can form what's known as an organolithium. Now, what's similar about these two systems is that the magnesium and the lithium centers, these are very electropositive. In fact, in many ways, we consider the alkyl groups bound to these centers as being pretty much carbanions. And so although we will draw partial minus charges on the carbon that's interacting with magnesium and lithium, for the most part, we often will consider the R group as a carbanion and your MgX as a counterion or cation. Similarly with the organolithiums, again, we often will treat these pretty much as though they are carbanions. And that's due to the highly polar nature of the bond between them. For the most part, we consider these ionic in a lot of ways, but the textbook will use some variation in how they show it. Nonetheless, we can treat these carbon nucleophiles as very strong bases and very good nucleophiles. Now, Grignard reagents and organolithium reagents, these carbon nucleophiles can react with a wide range of electrophiles, but these include carbonyl-containing compounds like ketones and aldehydes. And again, the mechanism is the same as what we saw for hydrogen nucleophiles. We have nucleophilic attack of the carbanionic species onto the carbonyl carbon, breaking the pi bond to form the tetrahedral intermediate, the alkoxide intermediate. And then in the presence of water, we will, or some protic solvent, but typically water, we will protonate the oxide to give us our final alcohol. Now, because these carbanionic species are not only great nucleophiles, but also really strong bases, it's important that we don't introduce the polar protic solvent until we ensure that we form the alkoxide intermediate. Otherwise, that protic solvent will just simply react with the carbon nucleophile. So when we're drawing our reaction arrow in a synthetic type question, it's important to separate that polar protic solvent from the use of your carbon nucleophile. So if we use the organolithium, it's reacted with our initial carbonyl containing compound first, and then once we've ensured that we form our tetrahedral intermediate, we would then quench the reaction with our polar protic solvent, typically water. Now we can also use Grignard reagents and organolithium reagents to react with esters, and that will produce a tertiary alcohol as shown here. So in effect, what we're going to be doing is adding that R group of the carbon nucleophile twice to that original carbon of the carbonyl. And so we see the same nucleophilic addition mechanism, it's just that we see it twofold. And very similar to what we saw for the reduction of esters is that we see the loss of a leaving group in that second step. So in the first step, again, we have the carbanionic species reacting with the carbon of the carbonyl, breaking of the pi bond to give you this tetrahedral intermediate. Now we said this was a high energy intermediate, and so it's more stable to reform the double bond and kick out this group as a methoxide. So the methoxide is acting like a leaving group because this species is so high in energy. Now the resulting product is your ketone, and then that ketone will re-react with additional or excess Grignard or organolithium to give you, again, a tertiary alkoxide, and then that alkoxide is protonated with your polar protic solvent, water, and that's going to give you your final alcohol. Now, when it comes to the reaction of Grignards and organolithiums with carboxylic acids, they don't work so well. And that's simply because you have a proton source with the carboxylic acid, and so the carbanion is going to simply react with that in an acid-base fashion to give you a proton transfer reaction and the resulting alkane. So in a sense, you quench your carbon nucleophile by adding the carboxylic acid. So anytime you have a fairly acidic hydrogen, like we see with the carboxylic acid or even with alcohols, these are not going to be compatible with Grignard reagents or with organolithiums. So in this section, we've seen different ways in which we can convert alcohols to carbonyl-containing compounds such as aldehydes and ketones. And we said that that primarily depends on the type of alcohol we're starting with. So if we have a primary alcohol as shown here, we know that we can use chromic acid to convert this primary alcohol directly to a carboxylic acid through some unstable or unisolable aldehyde, or we can use a more selective oxidizing agent or more mild oxidizing agent that will stop at the aldehyde stage. We also saw that we can reduce those particular carbonyl-containing compounds back to the alcohol using a variety of hydrogen nucleophiles, primarily sodium borohydride in some type of polar protic solvent, or using a two-step reaction where we first introduce lithium aluminum hydride, a much less selective reducing agent, but a much more reactive one, and then following that reaction with a water quench to give us our final alcohol. We also saw that if we start with a secondary alcohol and oxidize it, we will form a ketone. Now, there are various ways in which we can oxidize this alcohol to give us a ketone. We can use chromic acid, which is prepared in this way from sodium dichromate, sulfuric acid, and water, or we could use PCC in a chlorinated solvent to carry out the same oxidation. Now, going from the ketone back to the alcohol, we can use lithium aluminum hydride followed by a water quench, or we can use sodium borohydride. Sodium borohydride is effective in reducing ketones and aldehydes, so you have a bit of a choice depending on what you have available. We've also learned a new way to form a carbon-carbon bond. That is a reaction between an aldehyde, ketone, or ester with an organometallic reagent, such as a Grignard reagent or organolithium. And in that way, we're increasing the amount of carbon in our final product. And so in synthesis, this is very important. Like we saw in the previous section, alkylation was a way of increasing the carbon skeleton. Well, this is another way to increase the amount of carbon in your final product towards some synthetic target. And so we looked at a few examples where we can use Grignard reagents, which will then again form new carbon-carbon bonds to original ketones. We saw that that same reaction can be carried out with aldehydes. If you produce a chiral center, always remember that that can produce a racemic mixture. You're going to have two configurations because nucleophilic attack onto that carbonyl will occur from either side of the trigonal planar plane associated with that sp2 hybridized carbon center. And we saw if we use excess amounts of the Grignard reagent, we can carry out that reaction in two successive steps, if you will, to introduce that R group twice to that original carbonyl carbon, forming in effect a tertiary alcohol. So again, when working on synthesis problems, I find this chart quite helpful. And now you can see that we've covered the majority of the reactions on this chart. Specifically in this section, we've looked at a few new reactions that can convert alcohols to alkyl halides and vice versa. And we've also spent some time looking at oxidation reactions to convert alcohols to aldehydes and ketones, as well as the reduction reactions, which take us back to the alcohol. So if you have any questions about carbon nucleophiles or some of the synthetic strategies that we can use based on reactions learned in this section, by all means, send me an email. Thank you.